I'm going to give you a sketch of the proof of the following theorem. It says if you have a holomorphic function on an annulus, that means basically the region between two circles, then f has a Laurent series on A. So let's draw a picture here. And the picture is this. So here I'm going to have two circles. I'll make the circles in red, how about? And I'm centering them at the origin. This is R1, and a big circle R2. If you don't want to have them centered at the origin, you can actually move them just by a simple translation. So the way this theorem is typically proved is you just translate to the origin, prove it, and then move back. So I'm not going to worry so much about what happens over there. So I'm going to figure out, I want to take a generic point somewhere in here and call it Z. And I'm going to try to figure out what the Laurent series is by evaluating at Z. Okay, the way you do this is you first of all create some sort of a circle on the inside here. We'll call this one, sorry, I want to see what the book does. The book calls this gamma 1, and then we'll call this purple one out here gamma 2. It's called gamma 2. Okay, so what I really want to do is I want to use Cauchy's integral formula. But I can't quite do it right now because even though there's a whole bunch of stuff going on here, right, it's holomorphic between the red, and I have these two curves, I just need one region that makes sense. Well, to get that one region, what I'm going to do is I'm just going to add a little piece here going that way, and the overlapping piece going the other way. What happens then is you can imagine this just kind of slices it, and you just get one big rectangle if you were to unfurl it. So you've got purple border, orange, blue, purple. Right? So you can lay it out like that. And so we actually have a region right in here that is completely works well. You have a holomorphic function, so you can use Cauchy's integral formula to figure out that g of z, let's call it f of z, because I'm assuming that f is occurring at the origin, so this is after the translation. That's just going to be equal to 1 over 2 pi I times the integral around gamma of f of w over w minus z dz. Right? That's literally what it means. What you do is to figure out what this integral is, you take this value, plug it in here, and you get the result. And this gamma is equal to this bit right here. Like that, and then orange, and then blue. Right, this is what gamma is equal to. But notice, right, the orange bits cancel themselves out, so you really just have the integral around the blue part minus the integral around the purple part minus, because we're going in the opposite direction, minus the integral around the blue part. So this is going to equal 1 over 2 pi I times the integral around gamma 2 f of w over w minus z minus 1 over 2 pi I, the integral over gamma 1. And now I'm going to leave this for another screencast. It's just going to amount to figuring out these two values, what these two integrals are. And you're going to see that one of these is going to give us all the different positive exponents for the Laurent series, and one of us is going to give us all the different negative values for the Laurent series. So I'm going to stop here, and I'll continue in a second part. Thank you.